All right, recorded is rolling. It is Monday, January 29th. We're continuing optics. You guys remember last week we did things like EM spectrum, electromagnetic spectrum, color theory. We did a lot of reflection, refraction. We did ray diagrams. Right? So we're going to pick up there. Got some more details about refraction, some demos I want to show you guys. I gave you guys a page before I hit record, has some mirror puzzles on it. So we'll go through these 4 puzzles straight out of the Kahoot materials. Right? Then on the flip side of that paper are conceptual questions, and we'll do a Kahoot near the end of class. That'll be a wrap on today. All right, so do you guys remember last week we were talking about refraction? You guys remember doing Snell's Law lab, Snell's Law, with the lasers and whatnot? Right. And then, see, why is there refraction? Well, what kicks off refraction is the fact that light slows down in some materials, slows down in water, slows down in glass, and that kicks off this whole process that causes refraction. Whatever that last week, right? Now, the more light slows down, the more refraction is going to be caused. Right? So, how much light slows down in some material? It's called index of refraction. That's a material property. So for a vacuum, that's exactly 1. Right? It's like, what's the speed of light in a vacuum compared to the speed of light in that material? So for vacuum, it would just be C over C. So that's going to be 1. Right? In air, we can just round that to 1 because it's so close. Right now, if you're looking at like through a telescope, you think you can see better images if you're above the atmosphere than on Earth, right? Right. So that's why a lot of telescopes are like up in space. Right? Okay. Right. Oh, but now water. Okay, now we're getting a bit more exciting. Right. So drinking straw in a glass of water is definitely going to bend, right? Or glass. I don't quite have glass up here. We're about to look at glass, a bunch of examples of glass. But I remember last week it came out index of refraction was like about 1.5. You guys remember that? About 1.5 index of refraction of whatever glass we had. Right. I bet this is like some kind of, that sounds like glass, think glass right here. Right. So I'm able to get magnification because refraction, right? And then, ooh, diamond, like 2.42, right? Now, what about this? Here, let me throw you guys a question that's going to come back later today, right? Maybe in Kahoot, right? Suppose index of refraction of water is like 1.33. What if I have some kind of special glass that also has an index of refraction of 1.33, right? And what if I put this underneath the water? Is it going to magnify at all? No, there's going to be no magnification because, again, imagine that we're submerged. We're underwater, like exploring the depths of the pool. Like, yeah, it's the bottom of the pool. Then going from the water to the glass back to the water, there's no change in speed. Therefore, there's no refraction. This would look completely invisible, right? Like you might just think that you're going around here with like an empty metal ring. That's what you would think, right? Actually, that does tie to my next example. So I used to teach a forensics class, and one of the chapters they actually brought up index of refraction. So let me flip my screen over because I found some slides on the internet. That's exactly what I want to get at here. So somebody's presentation. Here's the story. Suppose there's some crime scene, maybe something like this crazy going on, and you find like little glass shards. And maybe you don't have a lot of evidence to work on, but you find these little glass shards at a crime scene. Like, if only I could match these glass shards to some source, right? I could crack the case, right? So I'm going to figure this out, right? Oh, well, what property glass could we look at? Okay, glass that might have different properties. It's got some color, got some, hey, it has some refractive index. Ooh, think about refraction. Look at there, refraction. You guys see some refraction going on, right? Okay, more refraction. All right, here's what we're going to do. We're going to take this little glass shard. How do you figure out what's the refractive index of this little glass shard? All right, guys, everybody look up here. Think about this. Right. And we'll put it in like different kind of liquids. And there's some liquid, I forget what it is, that if you change the temperature of the liquid, it'll change its refractive index a little bit. What if the refractive index of the glass is like exactly 1.51? And then if you can figure that out by submersing it in a liquid that's also same refractive index 1.51, guess what it's going to look like? Well, let's see, because I got a video example right here of exactly this. All right, you guys ready? You guys ready? So close. All right, so here, he's got 3 containers of liquids. The left liquid is water. The middle liquid is glycerin. I forget what on the right is, but it doesn't matter. Right. So let's focus on this one. You guys see he's dropping these glass beads? You guys see that? Right? You can clearly see them here in the water because glass about 1.5, water's about 1.3. Okay, so there's definitely a mismatch. Okay. How about the glycerin? Flint glass. Ooh. Borosilicate glass. Ooh. No.
Okay, thank you.
That was like the moment. Here, moment of truth. Ah. Do you guys see what just happened? You guys just happened? Right, when you guys got an advert, it disappeared. Right? I mean, it's there. It's there. Basically can't see it, right? Because there's that glass and that liquid have pretty much the same refractive index, so there's no refraction. Therefore, oh, it looks like it's invisible, right? That's it, right? Okay. And then here's a whole table of refractive indices, different kinds of glass, and all these numbers, they're all kind of about 1.5 something, right? I mean, I see like some 1.4s here. I see some 1.6s here. Okay. Oh yeah. Okay. Okay. All right. So there you go. There's a forensics application of refractive index. All right, let's do these mirror puzzles. Hey, you guys got your mirror puzzles? Again, I'm not gonna pick this up from you guys, but let's do this way. We'll read all 4 questions, then we'll go back over all 4 answers. I'll give you guys some time to see if you guys can figure this out. All right. First question. She's standing 1 meter in front of a mirror, a dresser mirror. 1 meter in front of a dresser mirror, and she's looking at the flower on her head, but reflected in the handheld mirror 1/2 meter behind behind this flower. Right. So how far back behind the dresser mirror does she see the image of the flower? So you guys get the premise here is she's looking in the dresser mirror. She's not looking at a direct reflection of flower. No, she's looking at a reflection of the flower. Right. So starting from the plane of the dresser mirror and going back, how far back then does you see the reflection of the reflection? Right. What do you guys think about that? I'm gonna narrow it down to 4 answer choices. Back to this about 5 minutes or so. So we'll come back to that one in a few minutes. So second question. Ooh, in order that you're able to see a full-length view of yourself, the minimum size for a plane mirror must be. Let's say, for example, if let's say, for example, if you are 6 feet tall, how tall a mirror do you have to see so you can stand in front of it and see your entire reflection? Do you need a quarter your height, half your height, 3/4 height? Do you need your full height? If you're 6 feet tall, do you need a 6-foot mirror? Right? Or does it depend on your distance? Right? Maybe I can't see my full self, so you step closer, further away, and you can. Right? Maybe something like that. Right? Just think about that a little bit. Get some time here. Think about that one. All right, third question. So this handheld mirror in front of her. What if she's trying to see her face? She doesn't see enough of her face. She wants to see more of her face. What should you do? Should she hold the mirror closer or further away? Or do both A and B fail and she just needs a bigger mirror, and that's the only solution. Right. And you know what? This one, let's try this. Let's do the empirical science version of this. Do you guys see that handheld mirror? You guys have it back there. You guys see a handheld mirror? Now, careful, it's two-sided. One side has a little bit of concavity, the other side is flat. Right? Go ahead, look at the flat side and try this out. Right? You see some, and then you guys can pass it around and try it out. Right? Maybe by the time we round back around this question, you'll have seen your face in the mirror. Hold the mirror closer, hold it further away, and see what happens to like how much of your face do you see comparatively as you hold it closer, further away. Right? And if you see that, you should probably see the answer to that particular question, A, B, or C. Which one it is? All right. Okay, and then the last one. That's why I'm going to throw the original color version on here because it's a little bit easier to see. Okay. So I got a couple of friends. One's on a bridge. One's taking a picture. Notice she's on a little bit of an elevated hill, maybe compared to. She's taking a photograph of her friend standing on the bridge. Which of these picture sketches, A or B, more accurately represents the photograph? All right, you guys ready to go with answers? You guys passing the handheld mirror around so everyone gets a chance to try that. All right, so back to question number 1. Ooh, the reflection of the reflection. Let's see, show hands, show hands. How many guys think the answer is A? Who says A? Who says B? B. Who says C? Who says D? Oh, I wasn't expecting that. All right, there were a couple of votes for a B. I'm gonna pick B. Right. So show you guys why. Let's start from this flower and go through the reflections one at a time. So the first reflection is in the handheld, right? And if it's just a plain mirror, then isn't it true the reflection is going to show up on the opposite side, equidistant from the plane surface, which is like right there? Is that the first reflection, right? And that is also 1/2 meter from the mirror, just on the other side. So this is 1/2 of a meter that way, right? Right, 1/2 meter. Okay. Okay, so that's the first reflection. Now she's looking in the big dresser mirror at that reflection, right? So reflection over reflection is, what is that distance right there? Is that 2 meters? Does that add up to 2 meters? Right. So when she's seeing that reflection, is that going to be 2 meters from this plane? Right. So that's it. It's 2 meters. 2 meters. Well, meters. Whatever. 2 meters. Okay. You guys got 2 meters? Right. How about this guy standing in front of the dresser mirror? Right now, this one. It's a good question right here. All right, let's do. Okay, stand in front of the mirror. How much mirror do you actually need to see your entire self? Let's say show hands. Show hands. How many guys say option A, quarter your height? Quarter. Who says a quarter? Who says B, half? B, half. Anybody say B, half? Okay. Who says C, 3/4? Who says D, you need your full height? Who says E depends on your distance? Ooh, that one's getting a lot of votes, right? The answer is actually B, right? Oh, yeah, say B. All right. Okay. Let's check out why. So, where does this guy see his image? Let me try to get this about right. So, he's got a fine nose here, a chin, and it's going about like this. Oh, foot here. I guess here's this. So there's this reflection pretty close to it. I guess pretty close to this reflection, right? About there, right? It's about equidistant, the whole thing from the. I don't know if I got it exactly right. It scooch him a little bit further to the right. I should have. Right. I think I got that. Okay, yeah. It bumped him a couple millimeters to the right. Right. All right. So you guys got that? All right. So I remember last week we did some ray diagrams. The first that we did was for reflection. I'm going to do something similar to what we did. Now, the ray diagrams we did last week, I went from the very top of the object. We're more interested in like what light is entering his eyeball. So he's looking in this mirror. He sees the top of his head and the bottom of his feet in the mirror, right? So let's do rays of light that are entering his eye as he's looking straight to the top of his head. Looks like there's the top of my head right there, right? Right. But that light ray actually came from boing, top of his head that way. Right. So that's not quite a horizontal line like we did last week, but kind of close, right? Okay, so about like that, right? Boing. There's one ray of light, right? Then he looks down and he's looking at his shoes. So let's have this guy look down at his shoes. It's like here he sees his shoes right there. Right. Now that came from a boing light ray from this direction. So about like that. You guys think? Okay. So there's two rays of light. Right. Boing, boing. Right. So that he can't see his full self. Right, you guys see that? Right. Okay. Okay. Now let's do some measurements. How tall is this guy? This guy is, you guys think about 3.1 centimeters tall? 3.1 centimeters?
Yeah.
Right? Okay. How about this little part of the mirror where he can see his entire reflection? Isn't it true? Guys, everybody look up here. I think he only needs that little bit of the mirror to see his entire reflection. Right? Right. Top of his head to bottom of his feet. How much is that? That is maybe almost 1.5, right? You guys see about 1.5. Right? In fact, if I scoot my reflection a little bit to the right where it actually should be, I think it'd be maybe 1.5, a little bit more. Ooh, guys, 1.5 compared to about 3 centimeters. Is that about half? Is that about half? Right? You guys think about half? Right. It's like half, right? Now, it's half for that particular situation, but a lot of you guys raised your hand and said you thought it might be E, right? Well, you can get them closer or back them further away. So it'll turn out that it's always these 2 points on the mirror to see his reflection. So, yeah, it doesn't matter how close or far away he is. And you can try this out in real person too. If you're ever standing in front of a reflective surface, I remember one time I was in an airport lobby. There was a glass wall. It was night outside, which makes like a mirror, right? And I tried this out myself. So I was standing kind of close. Say like, okay, where on the reflective wall do I see the top of my head and my shoes, right? And okay, well, there's a little mark on the wall there. There's a little smudge on the wall there, a little fingerprint. And I just started backing away, right? Started walking away, further away. What you'll notice is that where's the top of your head and your shoes in the reflection doesn't actually change depending on your distance. It's always the same spots. Like, oh, hey, there's the same mark on the wall. There's the same smudge, same fingerprint, right? So it's all the same locations, right? So I did mine. And you know what? That premise too, like why is it the answer B and not D, goes hand in hand with the next question, right? Which you guys might be seeing too. Is that mirror still going around? You guys still pass that hand mirror around, right? So try that. Right? Let's try this. Right. So as you get it closer to your face and then further, oops, I flipped to the wrong side. There. Closer to your face and further away, you can see. And what answer are you guys seeing? Or you kind of implied from the previous question. Let's see, show hands. A, B, or C. How many of you guys think to see more of her face, she should A, hold the mirror closer? Who says that? Who says B, hold it further away? And who says C, the only way is she just needs a bigger mirror, needs a bigger mirror? Yeah, needs a bigger mirror, needs a bigger mirror, right? So these two questions really go hand in hand, right? Same premise, right? However much of your face you see in this flat mirror is the same regardless of the distance you hold the mirror from your face. So you need a bigger mirror. Okay, you guys get there? Good. All right, and last question. Taking a photograph. Which one of the? All right, let me bring the color picture again. Let's take color picture. All right. Oh, which is more accurate representation of that photograph? A or B? Show hands for A. Who says A? Who says A? Nobody say A? Who says B? B. Yeah. All right. B. All right. Because option A is just you just flip the image upside down, right? But option B is, well, if you're sitting here a little bit elevated, you would see the reflection on the water, which shows the underside of the bridge. Yeah, B. Going for option B. Okay. All right, you guys good with those mirror puzzles? Yeah. Mirror puzzles? Yeah. All right, you guys ready for Kahoot? Kahoot. Kahoot time. Hey, pause this recording and flip over to Kahoot. All right, we're back recording. All right, you guys are on Kahoot. If you want to follow along with questions, they're on the back of the mirror puzzles. Right, same questions. All right, here we go. All right, on all these different materials. A lot of these you guys have seen from last week. A couple of these I haven't told you guys, so let's see if you guys can. Compared to the speed of radio waves, the speed of light. Spectrum right there, electromagnetic spectrum. One winner, the same speed. All right, so guys, all those electromagnetic waves, and people divide them into 7 different categories, from radio waves up to gamma waves, right, and visible lights in the middle, right? They're all electromagnetic waves are all travel at the same speed, right? Speed of light in a vacuum anyway, right? Right, so it's 3 times 10 to the 8 meters per second. Now they have different wavelengths and different frequencies, right? Maybe a little bit different properties, but they all travel at the same speed, right? Same speed. Right, you guys got that? All right. Chub Bob Serpent, which is fundamentally different from the others. It's sound waves, right? Because those other options, gamma, radio, light waves, like visible light, right, are all part of the electromagnetic spectrum, which are transverse waves that travel at the speed of light, can travel through a vacuum, right? But not sound, right? Sound is a longitudinal wave, like a pressure wave, travels about 1,000,000 times slower, and it needs a medium to go through, right? So yeah, it's like categorically different than those other 3. Got Isaac and Amora Josiah hopping in, but Judd Bob Serpent still in the lead. Difference between a radio wave and a light wave. Wavelength, right? Remember, same speed. The speed's not different, right? Another choice that would have been good if it was up there was frequency, right? You could say different wavelengths, different frequencies. That's also okay. Same speed. We got more Josiah, JP, Sophia, Chub Bob Serpent, Isaac. Compared to speed in air, the speed of light and water. Slower, there you go. All right, so it's from last week, slows down inside water, therefore it bends, called refraction. It's whole process. Yeah, that's from last week. All right, here we go. Glass is transparent to visible light, but not to what? All right. I did last week sort of tell you guys the ultraviolet, but I don't think I mentioned infrared. So there we're gonna go with both of those, right? So like what kind of materials can different parts of the spectrum pass through, right? Let's do another UV example, although but you guys said that anyway, right? Say you're going on a road trip across the states, right? And like driving all day, it's bright sunny day, and you're inside your car. Do you need to wear sunscreen inside your car? No, because the glass is going to block that. A lot of guys got that one. Yeah, infrared also. A lot of that'll be blocked by glass, right? But visible can grab the glass, right? All right, JP on fire to top. Clouds. Ooh. All right, so as let's say you're gonna spend a few hours at the beach, you and your friends, a few hours at the beach. It's like, oh, I should bring sunscreen. And your friend says, oh, don't worry, it's cloudy. It's gonna be cloudy all day today. Should you still wear sunscreen on a cloudy day at the beach? Yeah, right. Because a lot of that UV will go straight to clouds. Maybe not the visible so much, but the UV, yeah, zip through, right? And then yeah, you don't want a sunburn and cancer. Yeah, all right, JP points. Electron vibrates 1,000 times per second. 1,000 hertz. Yeah, frequency 1,000 hertz. That's what we're talking about. All right, you guys get that? Frequency 1,000 hertz. That's what 1,000 times per second means. I got Isaac, Amor Josiah, Emily, Bob Serpent, JP. How far is 1 light second? All right. So that would be the distance that light travels in 1 second. Now you guys know speed of light's like 3 times 10 to the 8 meters per second, right? Right. So in 1 second it would travel 3 times 10 to the 8 meters. That's like 3 times 10 to the 5 kilometers. Oh, hey, that's what that is. Right. Do you guys see too in the graphic I had thrown up there? The distance to the moon is, I think it's at 1.3 light seconds, right? So back in the Apollo program days, there was a good time delay between the astronauts and the scientists down in Houston. Okay. All right, here you go. All right, Chud Bob Serpent, take the lead. The distance light travels in a year is called 1 light year. Yeah, true. Right. So light seconds, light years, those are distances, right? How far does light travel in that interval of time? Right? Did you guys catch on the graphic? There was a star called Proxima Centauri, like proximate, like close, right? Which is the closest star to our solar system, right? You know, like far in the sun, which is on our solar system, right? Do you guys see? So 4.2 light years. If there's like, if we're sending out some kind of communication signal to that star, it would take more than 4 years to reach that star. Right. All guys, all the stars you see in the night sky, every single one of the stars is the light coming from the stars is years ago, right? Years ago. They're many light years away. But hop in the top 5. Amor Josiah, Isaac, JP, Bob Serpent. Colors on a TV screen. Yeah, color addition. Right. So you guys remember on your screen? Can I get this up here? Oh yeah. Get this over here. Right. Guys, if you were like an ant crawling around your cell phone screen, this is what it would look like, right? This picture right here. Right. Those 3 colors. Right. So here, see you guys doing this. If your phone screen is black, then what colors are lit up? None, right? If your phone screen has a white background, you go to google.com, you get that nice white background. That's what color pixels. That's all of them, right? The more that turn on, the more it makes like white light. Ooh, I got a tricky question for you guys. What about yellow? How do you make yellow light? Green and red. Turn on the green and red. Again, give you some yellow. Right. But yeah, color addition. The more bulbs you turn on, right, the more color you get. Right. Color addition. All right, I got Butter, Sophia, JP, Isaac, on fire. Chud Bob Serpent. Colors on a printed photograph. Yeah, color subtraction. Right, so like your color printer has what was it? Yellow, magenta, cyan, I think, ink. right? And if they all go at the same time, right, then that'll create a black color, right? Because every color it puts on subtracts the reflected wavelengths, make it darker and darker. Make a color subtraction. Jordan, Amora, Josiah, back at top 5. JP, Isaac, Chud, Bob, Soypant, on fire. When blue and yellow paints are mixed, the resulting color is green because. Yeah, there you go. Right, between blue and yellow, all colors are absorbed except green. Right, so we're talking about color subtraction, right, with paints, pigments, right? So, like, if you just have blue paint, then yeah, it'll reflect a certain range of wavelengths that includes blue, also includes green. Your eye just picks up the blue overall, right? And then yellow, right? Again, there's like a range of colors, right? But put the blue and yellow together, now it's subtracting even more. But the green is able to be reflected from each of those. Right? Yeah, so it just narrows down to the green. It's about like 500 some nanometers length. Right. All right, Emily, back in top 5. We got more Josiah, Emily, JP, Isaac, Chud, Bob, Soypant, still on fire. 3 primary colors for additive color mixing. Yeah, red, green, blue. There you go. RGB. Isn't that? Oh, do I have to bring this picture back? Hey, there's the answer right there, right? RGB. RGB. Colors on your cell phone. More Josiah, moving up. Chud, Bob, Soypant, still on fire. Difficult to tell a roadway from a car on a rainy night because the road surface. Ooh. Okay, so what we're looking for is diffuse when it's dry, it becomes a mirror when wet. So anything that's diffused, like most surfaces in this room are diffused, right? So light hits them and they don't act as mirrors, right? You can stand in any position, they kind of look the same. The wall looks the same regardless of the angle that you're standing at, as the light scatters in all directions, right? Okay. But you know, put some water on that road. Well, now that water is acting like a mirror. That's like spectral reflection. That's gonna follow. You guys see a poster up here that says law of reflection. Right. That's more like a mirror situation. Right. There you go. You guys saw the picture's not up there anymore, but showing like a wet road. It's all rainy. It looked like a mirror. Right? Jordan, back on top 5. Chud, Bob, Soypant, still in the lead. Refraction. Okay, so yeah, if remember, if some material has a refractive index that tells you how much the light slows down on that material, that'll kick off this whole process that results in refraction, right? So notes from last week, right? Now I know we're focused on like light and optics, but you guys heard an acoustic example last week. You guys remember Paul Hewitt's story of he was in the Scouts, he had set up a camp across a lake from there was another Scout camp across the lake, right? And the story went during the day they were shouting at each other, they could barely hear each other, but at night they could be whispering in their tents and they could hear all the way across the lake. And the reasoning had to do with when there was a temperature inversion, the sound got refracted right into each other's tents. So yes, that was an acoustic example. Right, so yeah, so sound can also refract. That's okay too. What'll happen? Some examples of that. All right, Isaac, getting the points. When you see a wet spot mirage on the road, you're most likely seeing an image of. Ah, all right, you guys got it. Sky is what I'm looking for. Let me get you guys a picture here. Flip the screen over. Let's do this picture. All right. So, oh, you guys probably saw the picture too, right? So, guys, when you're driving along and it looks like there's puddles on the road, except you drive up to them and they disappear. So they were never there. It was just a mirage. Do you see those on cold days or hot days? Hot days. It's like it's always really bright, sunny, hot outside. So here's what's going on. That asphalt is getting really hot, and there's this layer of really hot air right above the asphalt. Right? So okay, so you got some rays of light, say from the sky. Right? They would normally travel a straight line, hit the road, and then go scatter in all directions, and you see the dark gray road pavement. Okay, but there's this layer of hot air. They can refract and refract right into your eyes, and it looks like a mirror, like something's being reflected, like the sky's being reflected, like there's some mirrored surface. But it's not actually reflection, it's actually refraction. That's what's going on. Refraction. There you go. Refraction. All right, Jordan moving up. Chud Bob Serpent. Lead. Person standing waist deep in a swimming pool appears to have short legs because oh yeah, because science. Refraction. Refraction. Right. Points. Oh, I'm so sorry, my screen's frozen. Okay. I don't even know. Okay. I'm gonna have to get this thing. I'm so sorry, guys. Yeah. All right, recordings resume. Yeah, so I know you guys were playing this one blind, but hey, so some of you guys got it. Right? Oh, we talked about this one earlier. Right, shortest plane mirror, you can see your entire image, half your height. So if you're 6 feet tall, if you have a 3-foot mirror, you can see your entire self. The catch is you have to position the mirror in the right spot. Okay, right. So talked about that one earlier. Yeah, we did. All right, and I guess there's a luck of the draw if you got that one, because yeah. All right, moving on. When you look at yourself in a pocket mirror, hey, this was the next question that we just did earlier, and then hold the mirror further away. Yeah, see, same amount of yourself, right? And maybe you guys have seen that too as you're passing that mirror around, right? Same amount, same amount. See the same face. Oh, yeah. Why do lions look wavy at the bottom of a swimming pool when viewed from above? That picture right there. Why? Why that picture? Yeah, light refracts at different angles due to uneven surface, right? So if it was completely calm water and no breeze or anything, you wouldn't get that effect. There would still be refraction, but just wouldn't look all wavy like that. Right, there you go. Yeah, so uneven surface, what I'm looking for. All right. All right. All refracting lenses rely on light having. Ooh, there's a telescope diagram there. I see two refractive lenses. They lined up. There's focal point with the beats. Yeah, so looking for a slower speed inside the lens that kicks off refraction, right? Right, slower speed. Right. Hey, guys, what about this? Let's set up the last question. Guys, what if you have, I think we talked about this earlier. What if you have this here magnifying glass? It has a refractive index of, it's probably about 1.5, but let's make believe it's like 1.3. And you take this underneath the water, also refractive index 1.3. Does this cause any refraction from the water to the glass back to the water? No. And what does this look like? You guys remember the submersion method for identifying like the forensic identifying what kind of glass? Right? You're trying to match the refractive index, it turns invisible. When this look invisible, right? Okay. All right, now maybe it's not exactly that. Maybe it's 1.3 for the water and like 1.5 for the glass. Is this going to magnify as well underneath the water? That's the next question. And here's for the win. Here's for the win. All right, ooh, all right, we got Jordan, Amor Josiah, JP, Isaac, Should Bob Soy Pant, on fire, going for the win. A magnifying glass underwater will magnify how compared to in the air. Yeah, there you go. Not as much, right? So the difference in refractive index, say 1.3 to 1.5, not as much difference as 1 to 1.5. Yeah, magnify more in the air, just more of a change. All right, to the podium with the bronze, JP. Ooh, he's going to pull with the goggles. The silver, Isaac. And the gold, Doug Bob Soyband. Runners up, more Josiah and Jordan. All right, nice job. Oh, yeah. Take us to the bell right there. Wrap on today.